Lecture 2, Chapter 2 and 3. Okay, so far in the first introductory chapter, we have mentioned basics of or introductory to general embedded systems and the differences between microcontrollers and microprocessors and so on. And we have seen how microcontrollers are used in application-specific projects. So from this lecture on, we'll concentrate on the specific microcontroller. But before we get into this, I want to review some technology-related materials like IC technologies, CMOS, how chips are specified, and hardware and software terminologies before we get into the deep of the microcontrollers and AVR product families. Then we'll specifically talk about AVR itself, 128 architecture, and the pins and the instructions and how we can write an assembly program related to it. And we'll talk about the data address space and ALU operations and the status registers that we have got in ALU operations. Also, we'll slightly mention the assembler and assembler directives that we generally use in order to have some code segments and how the program memory is working, how we are fetching instructions. If you do remember in the first lecture, we talked about fetch, decode, execute cycles. So we'll see how AVR is running those cycles. And we will also see the differences between RISC versus CISC architecture features. All right, let's give a start and let's talk about the chip, ICs in general. Well, I'm not going to go into the details, but at least we should have an idea of what chip is. Chip is an integrated circuit. So what we generally have is the sand is, which is made up of silicon. It's converted into a die. So die with the patterns like printing a pattern or a circuit on a die, and we put it on a wafer. Okay, so as you can see, this wafer has got dies inside of it. Okay, so this die is actually what we have got in a single microcontroller or microprocessor. Okay, so a collection of these are manufactured on a wafer, which we call it silicon wafers, and then they are cut through and they are just mounted or put it into a package so that we can use on our boards. Now, in the early days, these were bigger circuits like a discrete components, and nowadays we are using silicon devices, which we are embedding millions or billions of transistors inside of it, and we can run different applications and different processes very fastly. So there are different types of packages and integration, like you might see it on the boards, like ceramic ones, the plastic ones, and depending on the size and their technology nowadays, they might differ. So what do we know about transistor technology? Now, CMOS is the most common used technology nowadays. We call it complementary metal oxide semiconductors. So what is this? This complementary metal oxide semiconductors, we have got two different transistor switches actually, where we have got on and off, ones and zeros. And they are complementing each other. So when one of them is zero, the gate is zero, it's activated, and we are allowing the charge from supply to go out to VDD, and the other one is deactivated. And when this one is off and this one is on, whatever we have got on V out is discharged to the ground. So this is a typical inverter circuitry that you might come up. And by using these transistors, we can implement NAND circuits, NOR circuits, and then AND circuits, OR circuits, and so on. Okay, so we can use this transistor technology by applying the Moore's law, where we can double the number of transistors inside of a chip every 18 to 24 months, and we can integrate more functionalities, and we can have more functionalities with a faster processors. So another important metric in designing these transistor technologies is the dynamic power consumption. So IC components has got their own dynamic power consumptions related with the capacitance of the chip, and the voltage, which is the supply voltage, and how fast we are switching on and off the transistors. So this is one of the important metric. Another one is static power, which is a function of leakage currents. So when the transistors are not switching, they still have some current going through them. So it's totally related with the supply voltage, and we have to be really careful as we are shrinking down the transistor. This leakage current or static power is becoming more important. And when we talk about embedded systems applications or any kind of mobile device applications, which we have to have a low power requirements in order to save some battery, we have to push the supply voltage or lower, and we have to have ultra low power devices, and which doesn't affect it from the noise and so on. Now, chip specifications in general. Now, when we talk about the chip specification, there are various specs, which you can find it on the data sheets, like architectural specs. What are the operating modes? What is the capacity of the memory sizes, the instruction memory, data memory? What kind of programming do they have? Can you use assembly or high-level languages? Instruction set is important. You have to learn or know it. And we are going to see specifically with Atmega 128, but this is what we are generally using in this course. There are also electrical aspects in the datasheet, like the supply voltages, because if you are using that chip on your board, you have to know these electrical specs or the characteristics so that you can create a power supply, and you have to know the DC and AC specs related to it. So if you want more information about this, you can find it in the 128 datasheet. Now, this is all you need to know about the chip specifications. I'm not going to go into the details of it. Now, let's talk about hardware and software terminology. So, in general, in a complete system, we have both hardware and the softwares. So, as an electronic engineers, we are more interested in the hardware side, and as a computer engineers, they're interested more in the software side. But both of these disciplines has to know each other, has to understand each other in order to develop a complete system. So what do we have inside of an hardware? Now, we normally start with the transistors or the silicon, let's say. Then we build up a transistor. From transistors, we build the circuits. The circuits then comes up at the logic gates or logic blocks. And then when we combine these logic blocks, we have an architecture of a microcontroller, for example, or DSP. So that's the hardware side. On the other side, where we have got the software, we start with the bit streams, the machine code. So we have the binaries that will activate those transistors, and the machine code, those instructions, object code, the source code, which is the programmer is writing. And we also have application development tools that we can derive the code over there. And also, of course, we have got an operating system or user interface or app menus and so on. So these are all working in a harmony that we can have a complete system. We can't have a complete system without one of these. Okay, so next thing that we need to understand is what is a code, what is microcode, what is assembly language. So there are some terminologies that we need to know. So assembly language, it's not like a high-level language actually, because in high-level language like C, Pascal, in assembly, it's more specific, but in C, Pascal, they're not like that. You can write C code for any architecture. But assembly codes, they have any special instructions for the assembly language, depending on the microcontroller or microprocessor architecture that you are having. And high-level programming, it's easier to follow, and it's easier. You might have a short way of implementing a function compared to the assembly. But if you understand assembly, you can easily derive high-level programming languages. That's why in this course, I generally focus on the assembly side. Now, a program that we generally writing in assembly or high level is called a source code. And then a program converted to the machine readable bit streams, hex codes, or the binary is called object code or machine code. These are translated by the compiler. And you need a compiler to convert these high level codes to an object code, or an assembler that we use converts the source assembly code to object code. Now, efficiency of these, when we talk about as a programmer, we have to have an efficient implementation. So, for example, if you are writing a code and it will take you, let's say, 10 lines of code, can you write it in 5 lines or less? This is important. So, efficiency in coding refers to the number of machine instructions required to perform a given task. Can you perform that operation in short tasks or not? So that's what's the aim of it. So when we are writing a code in this course, we try to aim for a efficient coding. So microcodes or microprograms. Now, instructions, as we have seen in the first lecture, are executed by the CPU. So we define exactly what we need to do. So the CPU fetches the instruction, decodes, executes it. Okay, so these are all well-defined steps. Now, then, once we have got the execution, there's a control sequencer, and we have got a microcode or microprogram. Okay, so a microprogram is written during the design phase of the chip and is normally not accessible. So it's not something that we can see it, it's on the manufacturing side. Now, the available hardware resources combined with the efficiency in microcode determines the number of clock cycles each instruction takes to execute. We will see this in detail, how we are writing a microcode in efficient manner, and we can easily calculate the number of clock cycles that we are going to have for the written program. Okay, so now we have an idea of what microcodes, microprogram, and some definitions about codes. Let's get into the microcontroller side. So most common microcontrollers, 8-bit microcontrollers that we are using generally, or 32-bit microcontrollers. AVR, PIC, HSC 8051 is the old one. ARM microcontrollers, 32 bits, and PIC 32 microcontrollers are still on the market, and they're used in most of the embedded systems. Now, what we are interested in this course is the AVR families. So we are going to look at AVR in more details. Now, AVR, we have got different types of AVR, like classic, mega, tiny, and special purpose AVRs, which they have a different specifications according to their codes. So, for example, at Mega 128, it means Atmel Mega Group. So the chip belongs to the Mega Group, and 128 is actually the flash. Okay, so 128K flash in Atmega 128. So Atmel Tiny Group 4 is the flash is 4K, and Atmel Classic Group and the flash is also 4K, that you can get the product family from their codes. So classic AVRs that you can find on the market, 8090s, 2K and 2K or 4K ROMs, you can find a different specification. So depending on your embedded system application, you can actually choose one. You can also find a different packaging option. So based on your board that you are going to design or use, you can choose different pin numbers and different packages depending on your needs. And Atmega families has got a similar specs with Atmega 8, 16, 32, 64, and 128. As you can see, they have got a different ROM capacities and data rounds and data EEPROM capacities. A number of pins are also important, which we are going to see in a minute, because number of pins gives you more functionality. for that chip. Like ADCs, they're all 8, but 128 has got 16 timers, 3 timers, 4 timers, 128 got 6 timers. And you can see a different packaging options that you can find on the market. Tiny is a small device compared to the Mega and Classic ones, where we have a limited ROM and EEPROMs, limited I/O pins. So if you are creating a smaller applications, you might be interested in the Tiny family. And there are also some special purpose ones, they are used for USB hosts, advanced PWM, or LCDs. You can use these specific products, which they are cheaper and they might hold less space. Okay, so what we are interested in is the Atmega 128. So this is the package and pinout of 128. Available options 64 TQFB or QFN. So pinouts, as you can notice over here, we have got timers, different ports, ADCs, serial communication ports, interrupts. As you can see, most of the pins has got multifunctionalities over there. Okay, so they can implement both timers and the counters, or sorry, interrupts maybe, like a normal input-output port, or maybe analog to digital converter, or like a normal port or a serial communication port. So these are all given for the Atmega 128. And you can see the pin descriptions over here, like port A. Now we have got a first function as I/O port, input-output port with internal pull-up resistors. Alternative functions we can use as a low byte data lines or external memory if you want to connect an external memory. And port B, for example, same as port A, I/O, and alternative function, output compare, PWM implementations, SPIs. Port C, also I/O port, or as an address high byte for external memory. Port D, I/O port, or as a timer, counter, user clocks that we can use, or input capture. These are all can be configured in port D. We are going to see them in a different chapters, how we can do these configurations for different ports. And port E also same, timer, counter, interrupts, so analog comparators. Port F, analog to digital converting or JTAG interface as an alternative functions. And we have got VCC, ground, external oscillators, and supply voltage for ADCs and programming modes and so on. Okay, so these are what we are going to investigate throughout the course and see how different ports and different resources in area are going to be configured.